Hello everyone, welcome to our presentation on matrix multiplication using 8085 assembly language. We are Team Texas here to present a project that shows the process and challenges of performing matrix multiplication using the 8085 microprocessor assembly language. Our team members Banu, Abhinay Harini, Brinda and Jagapriya has worked collaboratively on this topic to provide insight into the fundamental operations and logic behind this implementation. Background on matrix multiplication using 8085 assembly language. Matrix multiplication is a fundamental operation in computing integral to applications across various fields which include engineering, data processing and machine language. Implementing these operations in the 8085 microprocessor assembly language requires control over data, handling memory management, and instruction sequencing. In this project, we demonstrate how to perform matrix multiplication at the assembly language level. Objectives. Our presentation is structured around the following key objectives. Initial matrix addressing, set up initial matrix for matrix A and to ensure efficient memory access during multiplication. Compute element of matrix C using assembly instruction to calculate each element in the resulting matrix C based on the product of matrix A and B. Store result, efficiently storing the calculated element in the matrix C designed for memory location. Halt program, concluding the program execution safely once the computation is completed.
I will continue by discussing the program implementation for this multiplication matrix. We are going to load matrix A, or in other words creating matrix A by initializing matrix addresses. LXI is used to represent the registers. LXI H 1000H, it means load address of matrix A into register pair H, and move LH implement store low byte of A's address in L, move HL store high byte of A's address in H. In this process the implements load A11 into memory location 1000H, load A12 into memory location 1001H, load A22 into memory location 1002H, load A21 into memory location 1003H. This makes a perfect matrix in spite of this position. We have finished loading matrix A. Creating matrix B, LXI D 1010H, load address of matrix B into register pair D, move E D store low byte of B's address in E, move D E store high byte of B's address in D, like A matrix D11, B21, B12, B22 elements are stored in memory locations. Compute matrix multiplication using subroutines called compute C00, C01, C10, C11 stores result in matrix C. This is the overall implementation of how the program will execute.
So far we have looked at our initialization and declaration. Now let's come to our major part of the program. You can see this program. These commands are describe the operation that will be performed for each element of the resulting matrix C. First we should calculate C01. It means it takes the element of the first row of the A matrix and the second column of the B matrix. That means A11 and A12, A12 and B22. We are going to product all those things. It means A11 multiple A12 and A12 multiple B22. Then we are added this. Store the result in C01. It means it allocates the space element of the second place of the C matrix. Repeating this process for compute C10 and C11. Then halt the program. Similar operation will need to be repeated to compute the remaining elements of the result matrix C. So far we have determined C10 and C11. This slide we can see C10 computer. Here we can determine compute C10 as like as C00 computer. Here we can take A21 element from A matrix and B11 element from B matrix and multiple these two elements and store the result in A and also a C storage. Then we are going to multiply A22 and B21. Then we are stored in A matrix. Then we added these two result. Previous result which is stored in C as temporary. These result are stored in A. These two result are added. Then we are going to store it in C matrix. Then we are move A C. Return to main program means read to the main program. Then we are going to apply this process, repeating this process for C11 and C10, so that we have determined C11 and 10.
So move to the explanation slide. The first step is matrix addresses. LXIH, 1000H. Set the address for matrix A to 1000H. Move L, H and move H, L. Transfer the high and the low bytes of the address into registers H and L respectively. This set the address of matrix A in the HL register pair. Similarly, LXID, 1010H. Set the address for matrix B to 1010H. And LXIH, 1020H. Set the address for matrix C to 1020H. Here, LXI 1000H. This instruction set the address of matrix A to 1000H. Here, LXI is a load immediate instruction for the HL register pair. Move L, H and move H, L. This command stands for the high and low bytes of the address to registers H and L, setting up the address in the HL register pair. Similarly, LXID, 1010H set the address for matrix B at 1010H, and LXIH, 1020H set the address for matrix C at 1020H. The second step is compute C of 00. Call compute underscore C00 calls a subroutine that computes the value of C of 00, which is the result of A11 into B11 plus A12 into B22. Move M, A, store the result from the accumulator A into the memory location pointed to by HL, which is the address of C of 00. The third step is compute C of 01. Call compute underscore C01 compute C of 01, which is A11 into B12 plus A12 into B22. Move M, A, store the result at the address of C of 01. Then the fourth step is compute C of 10. Call compute underscore C10 compute C of 10, which is 821 into B11 plus 822 into B21. Move M, A, store the result at the address of C of 10. And the final step is compute C of 11. Call compute underscore C11 compute the C of 11, which is 821 into B12 plus 822 into B22. Move M, A, store the result at the address of C of 11. Now move to the conclusion slide. The first point is initialization. Set up memory addresses for matrices. This step set up the necessary memory addresses for matrices, preparing the data structure to store and access matrix elements. The next point is computations. Call subroutines to compute matrix elements and store result. This involves calling subroutines, which are smallest segments of codes or functions, to compute individual elements of the matrix. The result of this computations are then stored. The next point is subroutines. Compute individual elements of the result matrix by performing matrix element multiplications and additions. Subroutines are responsible for computing each element of the resulting matrix. They perform operations like matrix element multiplications and additions necessary for generating the final output. The final point is multiplications. This is a placeholder for the actual multiplication logic which you need to implement. Thank you all for your attention, and a big thank you to my team for their efforts. We hope our presentation has provided you with a clear understanding of matrix computation.